Hi there and welcome from Ventura, California to today's webinar, Dual Channel RTK for UAS, State-of-the-Art in Science and Capabilities and Benefits, sponsored by InsideGNSS, Trimble, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar is about hearing from these experts as they address the latest in the art and science of this dual channel RTK technology and how to benefit the most when integrating guidance, navigation, and control systems for a wide variety of UAS platforms. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all of our panelists. Now, we've invited you, along with over 320 professionals from around the globe, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or location, we are confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher, InsideGNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce General Poss, who will be moderating the main portion of today's webinar. So at this point, over to you, Richard.
Thanks so much, Lori. On behalf of the InsideGNSS and Inside Unmanned Systems team, I'd like to extend a warm welcome to our international audience for today's webinar. We're delighted everybody can join us today. In just a few minutes, our panel of experts will take us from the theoretical to the very practical to the state-of-the-art. And now I'd like to introduce our sponsor, Joe Carey of Trimble Integrated Technologies. Joe.
Thanks, Richard. I'd like to add my welcome to everybody in the audience. On behalf of Trimble, I'm really pleased that we're able to sponsor this webinar. Trimble's mission is to transform the way the world works. UAVs are helping to do that, and in many cases, they can do it better with the benefit of precision GNSS. I'm excited about the panel we've been able to put together. They're all experts, and we'll be hearing about both the how and why of precision GNSS in the context of unmanned systems. There's something for everybody in these presentations. We'll touch on some of the foundational principles of GNSS and RTK, as well as some more advanced topics. So thanks again, Richard. Let's get started.
Great. Thanks a lot, Joe. We're delighted to have you as a sponsor. Now, I want to turn to the webinar over to today's moderator, General James Poss. General Poss is the CEO of ISR Ideas, an intelligence unmanned aerial systems and cyber warfare consulting firm. He's the founder and former executive director of the Alliance for System Safety of UAS through Research Excellence, otherwise known as ASSURE. He is a leading expert on UAS, having helped design the U.S. Air Force's remote split operation system for UAS control and the distributed common ground for UAS intelligence analysis. We're delighted that General Poss can join us today. General Poss, the floor is yours, sir.
Richard, thank you so much for that kind introduction. And, you know, I got to tell you what, before we start, I want to mention that we're thinking about the 2,996 civilians killed and 6,000 injured from 90 different countries on 9/11. And I think it's very apropos that we're talking about this subject that is so important to, you know, the future of the world when we're talking about some bad things that happened to us in the past. Okay, now that said, yeah, I got to tell you, you're literally talking to the Fred Flintstone of precision GPS, precision navigation. You know, I got into the Air Force. The actual date is classified. It's in the early 80s. I'm not as old as I look. But, you know, back in the day, the Air Force navigated using the extremely accurate dead reckoning and occasionally radar, and really it wasn't until the mid 80s that we got into good old-fashioned GPS. And back in the day, which really wasn't that long ago, we used to consider a really good GPS fix to be about 9 meters. Yeah, maybe down to 3 meters on a really good day, which was great for us because for the Air Force, that meant that GPS-guided munitions would hit generally within the length of the bomb that we were dropping. totally changed warfare. I'll be honest with you, totally changed our response to 9/11, which was our first real coordinate-seeking weapon, GPS-guided weapons war. But keep in mind, all of the stuff that we achieved after 9/11, was done with that, on a good day, 3-meter accuracy. And I'll be honest with you, I thought that would have been good enough for civilians. I know that it was a great debate in the Air Force when we decided to release the codes that would allow civilians to get precision navigation, just like the Air Force had, and also get that 3-meter code. Imagine my surprise when I really started digging into this webinar and, talking with folks like Jay Tilley and Visual Intelligence to find that really the accuracy that you guys are talking about with RTK dual channel systems is not 3 meters anymore. It's more like 3 centimeters and below, sometimes down to the millimeter level. So I've been absolutely fascinated learning from these guys, and Inside Unmanned has really, InsideGNSS has really produced a fantastic panel for this. First off, we got Stuart Riley, who's the Director of Engineering for Trimble. He's going to go into some of the ins and outs of dual channel RTK and from a technical level to explain how they get that fantastic accuracy. Then we've got Howard Lavin from one of my favorite companies, Micropilot Incorporated, one of the world's leaders in making autopilots for drones. And he's going to explain the aviation applications of a really, really accurate dual channel RTK. And then finally, we got Jay Tilley, who's CTO for Visual Intelligence. It's got an absolutely fascinating example of how you can use dual channel RTK to get millimeter level accuracy out of sensors in 3D. So I'm really looking forward to this, Lori.
All right, so shall we get started with our first poll, General Paz?
All right, it sounds good. Here we go.
Coming up on the screen is our first poll here. We'd like to hear from each of you, and in this case, you can select all that apply, but we're going to ask on the honor system to give us your top 2. Question is, what qualities of a position can be improved by using a dual or triple band L1, L2, L5 RTK system versus an L1 only RTK system? And your choices, as you see them there, are acquisition time, accuracy, better tracking, effectiveness of error resolution. L1 RTK is good enough. Okay, 52% saying acquisition time, 85% accuracy, 44% better tracking, 56% effectiveness of error resolution, and 4% saying L1 RTK is good enough. General Paz, any thoughts?
Yeah, so I was going to go out and buy a L1 RTK receiver. I guess this just talked me out of it. It's kind of interesting, because I kind of put error resolution and accuracy in the same barrel. I really thought we would have gone with more acquisition time, but I guess, thinking about it, once you got to fix, accuracy is of the utmost importance. So maybe I'm not surprised. A little surprised only 4% wanted a single channel.
All right. At this point, let's go ahead and move on with our presenters. Over to you, General Paz, for the intro.
All right, and I've already mentioned Stuart Riley, who is Director of Engineering at Trimble. He's going to explain the technical ins and outs and explain why only 4% of people thought that single channel L1 was good enough. Stuart has been with Trimble in Sunnyvale, California since the end of 1995. He's currently a Director of Engineering responsible for the precision GNSS-based technology used across Trimble, as well as several GNSS product lines. Prior to joining Trimble, Stuart completed an electronic engineering PhD in the field of GNSS at the University of Leeds in the United Kingdom. And over to you, Stuart. Explain why only 4% of those folks thought single channel was good enough.
Thank you, General Paz. I'll try. So today I'm going to talk about dual band RTK. I'm going to start off talking about some error sources and challenges, talk about dual band or dual frequency, as I often call it, versus a single frequency GNSS. Talk about why the pseudo range is so important and give you some examples there. Some critical considerations. Start to explore beyond dual frequency or dual band into triple band, and then some of the integration tools that are helpful when you're putting this type of product into a UAV. So if you look at GNSS or GPS. What are the overall error sources? Well, you start with the atmosphere. The ionosphere is a delay, and it's frequency dependent. So if you have L1 and L2, you can actually correct it, at least for first order. There's tropospheric delays. They're the big atmospheric effects. And the satellites deliver ephemeris. That tells us where the satellite, or allows us to calculate where the satellite is at any point in time and what the state of the clock is. They, of course, have errors. And then there are biases on the satellites. L1, L2 biases and other biases in there. If you are just using plain GNSS, then inertia is not a consideration. But if you're trying to measure, for example, use GNSS in photogrammetry, you may want to know where the position is, the focal point of the camera. So for that, you need inertial. And inertial has a whole bunch of lever arms and angles, sign conventions, etc. It's very easy to get those incorrect. And then you've got the quality of the IMU, temperature effects, age effects, etc. Then onto the GNSS hardware. The antenna is really critical to the performance. What are its gain characteristics? Where is the electrical phase center of that? That's where you're going to get a measurement. That may not be where you think it is on the physical UAV. What's its jamming performance really in the LNA? Is that going to start compressing sooner than you would expect? And how does it handle multipath? On the receiver, tracking quality is absolutely critical, whether you're single frequency or dual frequency. While you're not using the pseudorange for RTK directly, use it indirectly to resolve the integers, and I'll talk about that in a little in the next slides. And then, of course, the carrier tracking, which is the fundamental measurement for RTK. Then the PVT engine, so how good is your position engine? And, of course, the receiver may have some biases. So we start with sort of mapping and GIS type accuracies, either autonomous, so this is where you're just receiving signals from the GNSS satellites using the pseudorange or the code phase, and that'll give you something in the meter, 5 meter level performance depending on the quality of the GNSS receiver and the state of the atmosphere for those ionospheric, tropospheric effects I mentioned. You can improve that a little using either local differential or SBAS, such as WAS, EGNOS, etc. And this is a system where over a satellite link, corrections are provided to try and correct some of those effects I mentioned earlier. And this can deliver sub-meter accuracy. But for many applications, you want to go even more accurate. And that's where RTK comes in. So here you have the pseudorange, which is represented by that sort of square wave there, and that's unambiguous. So you have a measure of the range to the satellite. There are some errors there, but you have an unambiguous measurement to the satellite. The problem is it's quite noisy. It's on the order, depending on the receiver, from a few decimeters up to many meters. But then superimposed on that is a carrier phase. This is great because the wavelength for L1 is 19 centimeters, and you're going to get accuracy about 1/100th of that, so a couple of millimeters of accuracy. The problem with it is you only know where you are in one cycle. You don't know how many integer cycles there are to the satellite. And the whole trick with RTK is to combine those two measurements to provide you what are those integers effectively to the satellite. We do it a little differently, but effectively to the satellite. So you use the pseudorange to effectively set those, figure out those integers, set that, and if there's no cycle slip, you can then position with the accuracy of the measurement you're getting from the carrier phase. So in L1, this is kind of a pretty complicated diagram, but we've got 3 satellites here. You've got one going up the screen, one to the right, and one to the bottom left corner. And what we're just showing here is where all those integer wavelengths superimpose. And what we're trying to find is where there are solutions, where it matches, that integer assumption matches the data. And you can see there are lots in here. You've got the green circle here, which is the truth in this example, but we've got lots that approximately meet that criteria because there will be noise on this signal. Now the green circle represents that pseudorange error that I talked about earlier. So basically what you do is you use your pseudorange, you set a region that you want to search, and then you search for all these candidates and monitor that over time. The problem with L1 RTK is because this 19 centimeter and because the pseudorange can be on the order of a meter or more in error, you have a lot of search candidates so it's very easy to get the wrong integer, or you have to search and wait for a long time to get the correct integer. With L2, what happens is you combine the L1 and L2 data, and there's lots of different ways to do this, but simplistically, you can get an effective wavelength in the 80 centimeter range, and so then you have a lot less search candidates, and so it's much easier to actually identify what the real candidate is. It's more reliable, and you get it quicker. So that's in a nutshell, that's how it works. Now, the green circle or ellipse I showed earlier, how do you set that? Well, that really depends on the noise of the pseudorange. So here's some actual UAV data that we took a while ago. So on the right, you see the flight path. It's got on this UAV, there's some pretty sharp bank angles because we want to try and get on track as quickly as we can. And so on the top plot, you see the C over and 0. So what you're seeing there are the dips as it's banking, a combination of some masking, but also the fact that the antenna has a gain pattern. When the elevation angle changes, or the effective elevation angle to the satellite changes, the gain changes, and so you see those dips. But at the bottom, we see that the pseudorange is pretty consistent across that and across the data set. And here we're seeing 36 centimeter standard deviation, which is pretty typical for a precision receiver. So what you want to do is take that standard deviation and have 3, 4, 5 standard deviations, which set one dimension on that search volume. Some of the critical considerations for single dual band GNSS RTK processing is really, are you post-processor or real time? So if you're real time, of course, you need a data link. You can't go forward and backwards in the data. There's no data editing that you can do like that. Versus post-process, where if you're doing something like photogrammetry, you may not care about the real-time performance, and you can log the GNSS observable data, maybe an IMU as well, and process that offline. If you are doing real time, then you've got a base station to set up. L1 RTK requires relatively short baselines because the ionosphere will decorrelate over a relatively short baseline. So L1 RTK, typically sort of 1 kilometer or so, dual frequency or dual band, 10 kilometers plus, we can easily handle. But you're going to have to set that base station up or use some public infrastructure that gives you real time. There is another mode, precise point positioning, or PPP. Trimble has a service, others do as well, and this is where the customer doesn't need a base station. You can get RTK type accuracies using a correction stream that the service provider, in Trimble's case, our RTX service. So this is delivered over the internet or over a satellite link. These are a set of corrections that allow us to do some similar processing to RTK. Fundamentally, the algorithms are quite similar, and this can get delivered just a few centimeters 2D in real time. One of the other challenges you'll have is antenna placement. I showed you earlier what happened when you bank. EMI can be a problem. We see lots of challenges where the electronics are very noisy on a UAV, and cables and are not well shielded. That causes issues. Code performance, I showed you on the last slide, that's really critical. What is the accuracy, what's the performance of the pseudorange or the code? On a single frequency, if you're just doing regular positioning, autonomous or differential, you can use data that's just frequency locked. For RTK, we need the phase information. So you need phase lock data, which is harder to achieve. You need a higher C over N0. So you could have a situation where you're getting an adequate pseudorange-based position, but you're not able to process it in carrier phase mode reliably just because you're not phase locked enough of the time. Radio link, of course, is critical if you're doing real time. You're going to have some sort of comm link. For your UAV, you're going to have to share that or have a secondary link to get the corrections over to the Now the spectrum, so dual band is really the focus of today, but GNSS is more complicated than that. So we think about L1 as 1575. A lot of us just think about GPS, but there are a lot of other systems that are all superimposed on that band. And GLONASS is in a very similar band, so it's relatively easy to process it at the same time. Down at L2, similar situation, although a lot of the newer systems aren't using L2 mainly because it has less protection. So a lot of systems today, we're using L1, L2, and L5. So we're actually using triple band in a lot of the newer products, and yet more are also using the E6, B3 band as well as things get more complicated. In terms of products, these are some Trimble products. There are many other competitors have similar sort of products on the market. But really what I'm trying to show here is the progression of the type of things that are on offer today. So you can start with a single antenna, GNSS only, dual band. In fact, the dual band here has some of the signals are in triple band. And those sort of systems are pretty small. That's 40 by 50 millimeters. That's a pretty typical size for a precision GNSS receiver. Then you can go on to INS systems. So the picture on to the right of that, the top right, is a single antenna GNSS dual band with an IMU that allows you to do attitude. And then we have dual band dual antenna systems that lets you get near instantaneous heading of the platform, and you can couple that with an IMU. So and all of these systems are, the biggest here is 60 by 100 millimeters, so pretty small and would fit onto a small to moderate sized UAV. We have integration tools. These are, I think, we feel very important to customers. We tend to put all of our tools inside of our web interface. That allows it to be cross-platform. Doesn't matter whether it's a Mac or a PC or a Linux system. They are available when the platform's deployed, but really we're expecting the system integrators to use this during their integration, and then often they won't get used. So we provide tools for setting up the antenna. It's important that to get the maximum performance out of RTK, that the receiver knows what antenna is connected. We have models embedded that can take some of the elevation dependence out of the antenna. We also provide for inertial systems a graphical view of the lever arms. We find that lever arms are often incorrectly configured. Either the axis sign convention is wrong, the angle sign convention. So as a user enters the lever arm, often from a mechanical drawing, it will actually show you how it moves from a sign convention perspective. That helps remove a lot of blunders. And then just my last slide here. So one of the other things is interference. A lot of what we see is interference actually from the electronics on the UAV. You can get situations where there's external interference, but a lot of it is due to poor shielding of the electronics. And so we provide some tools here, a spectrum analyzer-like view embedded in the web interface, so you can see what is actually happening. We also, if you've got data logging, functionality, we will log a lot of this information. There's also a historical waterfall type chart you see at the top right that will show you what any interference has done since the unit was powered up, and so you can go fly a mission and then look at this data afterwards. And that concludes my talk for today. So over to you, General Paz.
Thank you very much, Stuart. And I think that was a stinging rebuke to that 4% that thought they can get past with just a single channel. That was an amazing description. However, you did raise a bunch of issues that would potentially impact particularly the small UAS market. And very luckily, we have Howard Lavin here to describe just how Micropilot uses dual channel RTK and how they help their clients get around some of the problems that you brought up. So Howard Lavin graduated from the University of Waterloo with a BASc in electrical engineering and computer science, as well as a master's degree in computer science. He is the owner, founder, and chief executive officer of Micropilot Incorporated. Since 2004, Micropilot has been the world-leading manufacturer of professional autopilots for unmanned aerial vehicles and has worked with more than 1,000 customers in 85 countries. Micropilot autopilots fly a wide range of drones from fixed-wing, multi-rotor, helicopter, and transitioning vehicles. Howard is also chairman of the board of TelPay, a Canadian business-to-business payments processor focusing on automated invoice payments. TelPay has been helping Canadian businesses solve their payment processing challenges for 33 years and processed over $7 billion in payments in 2017. So Howard, over to you. Tell us how you use dual-channel RTK in the autopilot market.
Sure. Thank you very much for that introduction, General Poss. It's very nice to be here. I'm going to start with a very brief introduction to Micropilot. Then I'm going to talk about some of the advantages of RTK GPS from the point of view of the flight control system. I'm going to talk about how the RTK is integrated into a typical UAV, and then finally how the advantages of RTK will help improve the performance of your drone. So Micropilot makes autopilots for drones. We make professional grade autopilots. There are about 45 people working at Micropilot. About half are in software and hardware development, a quarter in sales and marketing and admin, and then the remainder are in flight test, technical support, and production. So we make a variety of different autopilots, from circuit board type autopilots to enclosed autopilots to triple redundant autopilots at a number of different price points and with a wide variety of functionality. We're located in Winnipeg, which is right in the center of Canada, and we are about 10 kilometers north of Winnipeg, where we have a flight test facility right outside our offices, and we operate under a Transport Canada Special Flight Operations Certificate. A big part of what we do, half of our employees are involved in product development, and we have a number of different tools that help us do that. We have GNSS 32-channel Spirent simulator, anechoic chambers, sophisticated hardware in the loop simulators, as well as a payload camera simulator. This is a picture of the part of our production floor, and so a lot of what we focus on for reliability is the equipment and techniques that can ensure the best possible reliability. So we have a calibration chamber. We use a single channel GNSS simulator equipment to test GPS. We also have environmental stress screening to help ensure that all the solder joints, all the many solder joints on the autopilot are reliable, and as well as conformal coating and underfill equipment. We have customers that fly all types of different vehicles, from helicopters, fixed wing, multi-rotors, and even a couple that are working with aerostats. So first thing I'm going to talk about is how the RTK will actually integrate into your UAV system. And so, you know, all RTK systems need some source of corrections. And one way that you can get those corrections is to have a base unit next to your ground control station. And that base unit will send, it knows where it is, and so it can figure out the error for all the different satellites. It's listening to the same satellites as the GPS system inside your UAV. It sends those corrections to the GPS system in the UAV, usually over the same data link that you might use or that you're using for your command and control. Now, one disadvantage of this is that the RTK base needs to know exactly where it is located so that it can calculate the corrections. So you must have that at a surveyed location. Now, another possibility is you can connect to an RTK correction service, and that RTK correction service will, again, via the internet, you can receive these corrections into your ground control station. Then they go up to the GNSS receiver via the autopilot, and that way you can have your RTK corrections. And finally, as was mentioned earlier, there are satellite-based RTK correction systems that will send the corrections directly to the GNSS receiver. And these are the have the least impact on the installation into your UAV system. Now, one interesting variation on RTK systems is the moving baseline system. And in this system, you don't know your absolute position. You just know your absolute position very accurately. You do know your absolute position, but the high accuracy is relative to some sort of a base station that is moving. So here the base station doesn't need to know exactly where it is because it's on the moving vehicle. And this is used for a lot of high precision landing and launch systems, and is something that's really only available on the higher end RTK systems. Now, a lot of people, so some of the advantages of the dual frequency RTK systems, obviously the position accuracy is a big one. But I think it's, when you see the position accuracy on a spec sheet, it's a little hard to know what that means. So if you're using a cell phone grade GPS and say you're getting 2.5 meters accuracy, that would correspond to the circle on your left. If you use RTK and we're getting 10 centimeters accuracy, that would correspond to the dot on your right. And actually RTK give you much better accuracy than 10 centimeters, but the dot would have been too small to see. In addition to the position accuracy, the better position accuracy, you also get much better velocity accuracy. And that velocity accuracy can help you with your attitude estimation. So the Kalman filter inside your autopilot is taking your IMU data from your accelerometers and rate gyros, fusing that with the position and velocity information from your GPS receiver, and providing you with an attitude so that your autopilot can fly and navigate your vehicle. And the better that attitude information, the more accurately it can fly your vehicle and the better performance you'll get. So having a better velocity, especially a velocity estimate, results in a better attitude estimate, which results in better performance. Another thing that has been mentioned is the time to converge. The difference between single frequency and dual frequency time to converge is quite dramatic, but also once you've converged to an accurate fix, you're more likely to retain that accurate fix. So if you're in a UAV and you bank into a turn, most likely you're going to have a constellation shift. So with a dual frequency RTK GPS receiver, it's very unlikely that you will lose your accuracy. But with a single frequency RTK receiver, it's much more likely. And for the UAV to be navigating around and always having to switch from high frequency to low frequency, it's just not very good for the overall performance. And another aspect, and I'm going to stretch the definition of dual frequency RTK to include all of the features you get with high performance professional GPS receivers, is multipath mitigation. And multipathing happens when the signal from one or more of your GPS satellites, rather than going directly from the satellite to your GPS receiver, bounces off some other object. Could be a building, could be the ground. And what you get with this is some sudden jumps in position. And this can be very concerning if you're, taking off, landing, or hovering near structures. And the higher end GNSS receivers do a much better job of filtering out these multipathing errors. And now I think it's back to you, General Poss, for our next section.
Absolutely. And I think, Lori, we've got time for questions, do we not? Can you confirm or deny that?
Sure do.
Okay. All right, so we got quite a few questions out here, and I'm gonna let me just yeah, Howard, you did a great job of explaining it, but we've got an audience question here that talks about okay, given the fact that you're in a highly dynamic and Stuart, feel free to jump in on this as well. You're in a highly dynamic environment in a UAS. You're constantly, yanking and banking and turning. How does that affect the PLL phase lock on some of these high precision receivers? If you're constantly turning, you're constantly moving, is it really going to affect your position this much? Howard, if you wouldn't mind taking first hack at it, and Stuart, I'd be interested in your opinions as well.
Sure, but this is actually a question that's much, much better directed to Stuart. I know how the UAVs fly, but I don't know a lot about the internal workings.
Okay, talk to me. What is this a problem?
So do you want me to take this? This is Stuart.
Yeah, I think that was a hard no from Howard. So
Yeah, okay.
you got to save us here.
So yeah, the acceleration, the dynamics you see on a UAV are really not that challenging. For many years, we've had simulation scenarios that we used to go up to 6G in circles, and we really do not see any problems. We have a lot of margin. More recently, one of the things we do see on UAVs are some of these catapult launchers. We've instrumented them with accelerometers and see 6, 10G for a very short period of time, maybe more. And so we've certainly reviewed our tracking loops and can easily track through that. One of the ways we've done this is to take missions, post-process them forward and back, so GNSS and INS, get a truth out of it, and then rather than contrive a scenario in a simulator, use that truth data into a simulator and replay to look at how the system performs. So we've done a lot of that. Other challenges, of course, are the TCXO. So very low cost TCXOs, you're going to have acceleration, you're going to have some vibration. They have a lot of G sensitivity. So key for a precision unit is to make sure that it's got a good TCXO which has low G sensitivity. And of course, while we're talking about UAVs today, we've got a lot of experience in other markets where you have high shock in terms of construction and other applications. And so we've used all of that information. So I would say for a well-designed phase loop, UAV dynamics do not really cause a problem. Over to you, to General Foss.
Yeah, well, and I think you just presented a challenge to a lot of remote pilots out there. I think they're going to all go out and see if they can't maneuver to break that lock, but excellent stuff. Okay, Stuart, I'm going to keep you in the hot seat again, if you don't mind, because we've gotten 2 questions on this. Can you explain the difference in accuracy between DGPS and RTK, precision nav, DGPS being differential GPS,
Sure.
code-based positioning, and RTK being real-time kinematic? What's the difference in the system shortly, and then what does that mean on the ground as far as accuracy goes?
Yeah, so yeah, I mentioned some of this in my talk. So differential, this is where you're really using the pseudo range, or we often call the code phase. And so that measurement, depending on the performance of the receiver, we were seeing 30-something centimeters, 36 centimeters, 1 sigma, just as an example. We certainly see lower than that. I've seen receivers out there that have several meters. So that's the accuracy you have on that measurement. Now, you can smooth it. But the way differential works is you send some corrections from a base to a rover, and you essentially assume that everything's common mode and cancels, so the orbital error, the ionospheric, et cetera, et cetera. And so there you can certainly routinely get sub-meter, not deep sub-meter, not centimeters, but you can certainly get 50 centimeters at the 1 sigma, maybe a little bit better sometimes if everything's well behaved, where on a lower performing GNSS, you might be at the meter, 2 meter kind of level. Now RTK, that's where we're using the carrier phase. So we use the pseudo range to figure out the integers. Then we transition to the carrier phase. That measurement, the measurement of the phase lock loop is good to a millimeter or so. Now you don't quite get that accuracy because you have multipath and other systematic biases and other challenges. But you can certainly get a centimeter or 2 2D at a 1 sigma sort of level. So does that answer your question?
It certainly does. Very eloquent explanation. Okay, getting a couple questions about what are the considerations in integrating precision GNSS into a UAV. And Howard, I know you covered some of them. I just wonder if you can expound on that. Particularly, we've gotten another couple of questions about antenna placement as a factor of that. And I do know it's challenging as is to design a UAS that can, just have a propulsion system and, a battery and all that. But when you're faced with coming up with additional real estate and grounding and shielding to cover an RTK system, what are some of the considerations you're seeing with your clients?
Sure. Well, I think as it's becoming apparent, there are many different flavors for GNSS. And so one of the really important things is to understand what your goal is, what data you're trying to collect, and how you benefit by the improved accuracy, and make the choice of the flavor of RTK GNSS based on what your data collection requirements are. But once you've got the GNSS and you're integrating it, yeah, there are quite a few considerations. RF interference, as has been previously mentioned, is a really big one. You got a whole bunch of electronics packed very closely together on a typical UAV, and every piece of electronics is an RF transmitter, and that can not only interfere with and prevent you from obtaining a GPS lock, but it can also degrade the accuracy of that GPS lock. Vibration is another issue. Again, as Stuart mentioned, the crystals on the GPS receivers are susceptible to both G and vibration, and so that can affect the accuracy of your lock, as well as again, the antenna. The lower quality antennas that you typically get away with your cell phone grade GPS receivers are not going to be appropriate for the higher accuracy. So overall, it's a more demanding installation, and but because of that, you get much higher accuracy.
Okay, that's a great explanation. And I'll be honest with you, I've found with a lot of my clients, there's some just aviation 101 problems out there. Like a lot of folks want to go to some type of non-conductive material for the body, vice lumen or whatever, and people are just finding out problems with getting their systems to ground, let alone some of the big stuff that you mentioned there, Howard. Okay, well, Lori, correct me if I'm wrong. I think we're out of time for questions now, and we're going to go to another survey. Did I get that right?
That is correct. And folks, coming up on your screen is that second poll question. And again, we're asking you to pick your top two here. What are the most common issues that impact your position fix? Multipath, jamming, spoofing, atmospheric interface, or other environmental factors such as signal obstruction, radio interference. There you have it, 81% with multipath, 14 jamming, 4% spoofing, 40% atmospheric interface, and 63% with other environmental factors, signal obstruction, radio interference. How'd that stack up, General Poss?
Well, the important thing is apparently I beat Richard in the argument there, because jamming and spoofing are way down. Holy cow, multipath. I didn't think it would be that far up. I'm assuming that's because a lot of folks are doing a lot of urban work, and you're getting a lot of multipath distortion out there. Who knew?
Well, we'll go ahead and pass it back to Howard.
Okay, thank you very much. So again, now I'm going to spend a little bit of time talking about how the better accuracy of dual channel RTK can be used to improve your the actual flights of your UAV or flight performance. Now, obviously, if you're hovering close to an object, doing some sort of inspection, having a better position hold lets you remain much closer to that object, and also lets you collect data more accurately about or know more accurately where you're collecting data about that object. One place that makes a very big difference is in the recovery of, or the landing of a fixed wing UAVs. Now, the latitude, longitude, the position error from side to side doesn't make that much of a difference. It's really nice to always land your UAV with the nose wheel on the center line, but usually there's plenty of room side to side. Where it makes a really big difference is in the length of room, the amount of room, distance you have to provide for recovery. So if you're designing a fixed wing UAV, you obviously want to make it low drag and to have a very shallow glide slope. And that's great when you're flying, but when it comes time to land, this can become a problem because it really magnifies small altitude errors. So as you can see in this diagram, we've got two UAVs that might be at one of two altitudes. And if you see the landing position difference between those two UAVs given the same glide slope, you can see it's quite a bit larger than the altitude. So, you know, small numbers of meters of error can become many tens of meters of error in your touchdown point. Now, of course, there are other ways to get an accurate height above ground. When you're landing, there are laser altimeters and radar altimeters, but these have some disadvantages. The first is that the ground before your touchdown point is often not smooth. It can be really messy to have to try and deal with hills and trees and other obstructions that are going to affect the measurement from the UAV down to the ground. Also, especially with the laser altimeters, there are environmental conditions such as fog that mean that will obstruct the laser and will prevent you from having an accurate measurement. Also, some types of surface conditions like lakes or any body of water, or sometimes even very tall grass can make it difficult to get a good altitude from a laser or a radar rangefinder. Another important time that the higher accuracy of the dual frequency RTK comes into play is any sort of a launch or recovery, especially if you're moving at the time. So, you know, if you want to recover into a small net, it's pretty hard to do that with the accuracy of a cell phone grade GPS. You need basically an enormous net. Or if you want to land your UAV into some sort of box, which is quite popular these days, again, you need position accuracy that's much greater than the normal cell phone GNSS accuracy. Also note that in both of these situations, there are lots and lots of opportunity for multipathing, and the consequences of multipathing are very great. If you're a few feet above your landing point and suddenly your GNSS receiver is telling you're 3 meters to the left, could be it doesn't end as well as you'd like. So, you know, anytime you're dealing with these very challenging situations, the more professional grade GNSS receivers are very important. Crop spraying by drones is also something that is much in the news these days or talked about. And here, it's really impossible to do a good job of a crop spraying without the higher accuracy. So on the right, if you have a regular GNSS, the booms on the typical spraying vehicles are usually shorter than the accuracy of the GNSS receiver. And so you're not going to be able to spray the field properly because you'll end up with all kinds of gaps because the accuracy just isn't enough. Whereas on the left, you see the type of spray pattern or the ground track you'd get with a dual frequency RTK, and you know, minimizing the overlap necessary to ensure that everything's covered is very, very important, and that's something that RTK accomplishes nicely. Also, being able to do surveying flights without ground control points, not having to set out a whole bunch of ground control points and survey them is a big time savings and makes the whole operation more efficient. And finally, there's a type of GNSS receiver where you can use two antennas and it will give you a heading. And from my experiences, compasses are horrible things. You know, you get too far north, you can't use them. The current flowing through your to your motors will change your heading. Even changing a payload or changing the batteries in your UAV, and you have to recalibrate your compass. And so by using a dual antenna, dual frequency RTK GNSS receiver, you get rid of all these problems and at the same time end up with a much, much more accurate heading. So thank you very much for your time, and back to you, General Poss.
Okay, thank you very much, Howard. You know, you had to diss the one thing that I fully understood, which is compasses. I don't know how to take that, but anyhow, we'll just change subjects. How's that? All right, and we're going on to what is, I think you're going to find is a fascinating presentation from Jay Tilley, who is CTO of Visual Intelligence. And Jay is going to talk to us about how RTK GNSS is so important for getting possibly millimeter level resolution 3D models made with their proprietary sensor. Mr. Jay Tilley is a former Air Force officer, a fellow vet like me, senior engineer and executive with over 30 years experience in remote sensing, mapping, and GIS. His expertise includes collection systems design, processing systems, and intelligent analytics of remote sensing data for government and commercial purposes. Mr. Tilley has held vice presidents of Resource 21, has been the chief technical officer for PGTEK and Visual Intelligence, and general manager of the Sanborn Map Company. He's also held many other positions across the intelligence, GIS, and mapping industries. So Jay, over to you.
Well, thank you, General Poss. So I'm going to take you through a walk here from discussing positional accuracy, but really focus on the market value of that positional accuracy and where accuracy plays in creating value in a lot of the applications of UAS systems. So as a start here, let you know that Visual Intelligence has been around for about 15 years. We are really a technology company. We focus in on what we call imaging arrays, so arrays of cameras, and we've done a lot of work both on aerial and UAS platforms recently to prove out the technology and make it a substantial contributor to the resolution and accuracy that can be achieved from a UAS system. This slide basically illustrates kind of the life cycle of what we do. We basically fuse cameras into what we call a metric super sensor. So we basically take cameras that have a level of performance, put them together with multiple cameras, and achieve even better performance. The cameras can be configured in multiple ways, color, infrared, high resolution, wide field, which is one of the values of the array, is because we can kind of change this out and really trade off a lot of parameters that typically a single camera struggles to do. And of course, multi-platform, be able to put this on different types of platforms that accomplish different mission needs. The end game, though, working through our software, is the product. Now I'm going to be spending quite a bit on product in terms of discussing accuracy and where accuracy plays in terms of value. To do that, I'm going to first walk you through a workflow, and then we're going to talk about the difference between relative and absolute accuracy. In this case, data, of course, comes from the UAV and is processed in the field, and that data includes GPS signals are sent up to our cloud processing system where all the magic happens. In the production engine, we are able to take that data and produce what we call a virtual frame. And a virtual frame puts an array of cameras together to make it look like it's a single camera, but with the advantages of redundancy, in the solution for the virtual frame, we end up getting better positional accuracy as we move into 3D models and ortho products. Of course, the point cloud, as I'm going to say a number of times, is not the end game. It's actually what you can do with that point cloud in terms of 3D models, CAD models, and other use cases that then have much more a multiplier value, I would call it, as we move into the various industries. But first of all, what is positional accuracy? There's a lot of error sources. We've discussed a number of those today. They flow down to these metrics that we like to call accuracy in terms of horizontal or vertical or circular radius, some types of statistical distribution, and we quote those accuracies for a system, particularly in terms of relative and absolute accuracy. Relative accuracy means I can measure something on the ground. So I've got enough of a calibration that flows down to ground objects that I can make measurements horizontally and vertically. And of course, absolute is where is it on the ground. These are very different concepts. They interrelate. If you don't have good relative accuracy in your data products, the absolute accuracy doesn't help a whole lot. So you've got to have really good relative accuracy, and then you can really capitalize on the absolute accuracy that the dual RTK gives you. So I'm going to be talking about both of these concepts as we move forward in the presentation. One of the key drivers, why do we need millimeter and centimeter accuracy? As a matter of fact, we talk about DoD targeting, and you heard numbers like meters earlier in the talk here. Now we're down to centimeters, want to be able to make those kind of measurements. But the commercial industry is pushing us way farther than that. We're into sub-millimeters and millimeters in terms of our relative accuracy, and centimeters in terms of our positional accuracies. And the reason of that, of course, is the information value that we're trying to relate from an image or a 3D model to the value of that model in terms of describing it as an asset, describing where it is, if we're doing maintenance on it, if we're trying to locate it, trying to understand how to replace it. We have to understand that physical object. And in many cases, that physical object can't be understood until we're down into the centimeter, millimeter range with any kind of high accuracy. So how do we get the high accuracy? So in our case, we combine the sensor and the processing to get good relative accuracy, which is shown more on the right side of this, or the left side of this diagram, and then of course the absolute on the right side. To get to the high relative accuracy, factory calibrations and infill calibrations are mandatory. UAS systems are not necessarily the most environmentally friendly systems. They tend to deal with different thermal and different lighting conditions, and that has a substantial impact on these very small inertial mass systems. So factory and in-flight is really important. We calibrate every exposure, in fact. On the processing side, taking advantage of the image model, the interior, what we call the interior next door orientation, the distortion, correcting for lens distortion, extremely important if you're going to be getting accuracies down at the centimeter, millimeter level. We also have to generate a surface model because we have parallax issues, which means that we can't, that we see things differently through, if you close your left and right eye, you see things differently close up. Same thing happens on the UAS system. So therefore we have to have a very good DSM so we can understand the relief of the objects, if they're a cell tower, if they're oil and gas Christmas trees or ground areas or any other type of infrastructure. We have to have a DSM. And then we do a thing called a virtual frame where we take it even further and do bundle adjustment of our array cameras to produce the higher accuracy. So all of that together is what's needed to get the high pixel relative accuracy. And when we quote things in terms of pixel, so what does that mean? So if we have a millimeter ground sample distance or we have a centimeter ground sample distance, that means that our relative accuracy is 2 pixels or better at that ground sample distance. And then we get to enjoy the RTK GPS systems, the dual band systems, and get down to the absolute accuracy that relative accuracy affords us. So now we're in the 2 centimeter range for absolute accuracy as well. So you put those two things together, you now have a full capability to describe what a physical object is in terms of its size and where is it in the earth. A major step to achieving accuracy, though, is your image quality, because we're relying on the matching of images to decide where a pixel lives on the ground. This illustration from left to right shows a 2-inch resolution, which typically can be attained at 200 to 400 feet above ground level with a wide field system, getting all the way down to 1 millimeter resolution on this oil and gas Christmas tree, driven by the need to read serial numbers, to be able to measure bolt sizes, bolt patterns, and so if we're trying to understand an asset, we have to be down at this level to correlate it with a catalog and judge the type of asset to high accuracy, since a lot of these things are built by different manufacturers, can be swapped out, etc. So image quality, very important. Of course, a lot of cases, we're generating lots of pixels. The time to process those and get to a meaningful answer is extremely important. This timeline shows one illustration of getting to an urban building, and where the processing is automated all the way through to what we call a vector mesh model. And so just to be clear, we have point clouds, we have these vector models, and then we have what we call an edited vector model. You'll see over on the lower right side. The path to that is mostly automated. We do have to do some manual editing on our final model, but the payoff for that is getting down to data sizes that are 5 megabytes versus many, many hundreds of megabytes. And the most important thing is maintaining the accuracy. So as we go through this whole process, we maintain the integrity of the relative accuracy so that measurements can be made on these models. And the reason to get it done to small sizes so we can move these things around quickly. Now, a lot can be done in parallelizing. This is done on a Alienware kind of class laptop system. If you parallelize this in the cloud, getting to minutes to an hour is possible. But the key point here is that it's nice to have accuracy on data, but you got to be able to get it quickly. And so those considerations are important too. So I was going to hit a couple of use cases here. There are many of those. Ones I'm not going to hit on is precision ag survey and mapping, which was touched on a bit earlier, also very important for relative and absolute, as well as the DoD intel use cases, persistent surveillance, tracking vehicles, for example, on a wide field through full motion video, or training and simulation, all demand high accuracy. But for this purpose, I'm going to focus on telecom and oil and gas. And what I'm going to highlight first is the process to get there. What this diagram shows is that largely the after collection, the data processing is automatic. So the handling of the calibrations, the handling of the images, the image matching, the corrections for lens distortion, the corrections for radiometry, and then setting up the, and you see here there's a Pix4D. We've used context capture. We've used lots of different algorithms for our DSM. But it's all automated. When we finally get to a point cloud, and then we move into our modeling space where we actually generate our mesh models and our CAD models. The CAD model is really the output product. The CAD model is positioned accurately because of the point cloud. We have absolute information, we have relative information, and that's the success tool by which we can compare that item that we've measured to a catalog. This illustrates that in a pictorial way. So from left to right, we have a 3D point cloud that's made from centimeter imagery. From that, we generate a CAD model. The CAD model is positioned in terms of the point cloud and the imagery, and then it's finally textured with the imagery to generate a 3D model. So the end game here is the 3D model with ability to make measurements. Now, a key point to be made is if you look at these antennas over on the right side, a lot of times you can't tell what that antenna manufacturer is or what its capability is until you look at for example, underneath there, you have a number of connectors and cables going into that antenna, and the number of connectors and the size of those cables actually really define what that antenna is from a typing asset standpoint. So telecom, to a large extent, is pushing the need for high relative accuracy in order to type components and type cables. So if you're wondering why telecom is pushing the envelope, that's one good reason. And of course, what we end up doing with this is taking this data in an interactive environment and be able to go into an asset system and be able to type all the components in the system, be able to describe what they are, where they came from, et cetera, so that a maintenance plan may be made, or a capabilities plan for a tower in terms of what it's capable of doing can be made. Investors and others alike really like this information. Over to the oil and gas side, similar scenario. In this particular case, we want to be able to read serial numbers. We want to be able to read gauges. We want to essentially do an inspection down to the physical level. This is also a reason why we're pushing the millimeter, centimeter, and the positional accuracy is extremely important as well. We want to build a CAD model that's good to centimeter level, and as you can see, there's a lot of repetitive things on this, a lot of bolts, a lot of valves, very repetitive, so knowing where those items are in space as well as the physical dimensions is really key to typing that asset and being able to support the oil and gas maintenance life cycle. This shows an illustration of going from a wellhead that this was collected at about 100 feet from a UAS system. We have designs that can go to 1,000 feet and collect centimeter and sub-centimeter accuracy to produce those well size. So it is possible to do it. Calibration, of course, and paying attention to details on your UAS system is key to being able to do this. But we can cover that in questions if you like. This shows another illustration of the value of various types of resolutions and accuracies. In this case, knowing where all these various pipes are on this is the frac well site. Knowing where these are and what specifically, if you're going to direct the maintenance person to go fix something or we're going to replace something, we would like to do a lot of that stuff with the minimum field visits as possible. That's one of the value propositions, is that the more we can do from a flyover and help someone plan and architect their maintenance, their control of the site, compliance, the less you have to do in the field, and that saves a lot of cost. Switching gears to DoD Intel applications, there's really two major use cases I'm going to touch on. One is I call tactical image analysis. This is more of what we call a targeting case, where we want to assess a site or a building or facility to a degree to support an operation. And then on the left side is persistent surveillance. We want to fly wide field but high resolution. Arrays are really good at both of these things. The wide field high resolution is great because I can add cameras, and as I add cameras, I don't necessarily have to compromise my resolution like you may have to do with a single camera system. But I'm going to focus mostly on the tactical image side and show you some value of that. In this case, we can generate a point cloud, which is automated all the way from collection, then automated to a mesh model. You see that mesh model where these are all now vectors that have had textures applied to them, but the key thing is maintaining the accuracy through this. So there's constraints put on the mesh model to make sure that edges and everything line up so we can make them measurable. And then finally we get to an edited mesh model, and this has actually had some manual work done on it because 3D models are never perfect. They always have a little bit of errors in certain places that you don't like them. So if you want them perfect, you've got to go in and do a little bit of work. So that's kind of the life cycle walking through of that. And the value of doing that is I can now make some really good measurements on a very small data size. In this case, we're measuring windows and doors. We're also correlating the images to the 3D model so you can go back and forth. So a lot of cases the image retains an integrity that the 3D model doesn't always do perfectly. So we want to maintain that correspondence. However, the accuracy is definitely maintained. And things like low-hanging cables, when you might not be able to see these around a building, is particularly important, which means that not only your resolution's got to be good, but your relative accuracy has got to be good, so you can make those measurements. And if you're a helicopter pilot flying this, you better hope that the absolute accuracy is really good, so you know exactly where that object is, particularly at night. So that kind of drives home, I think, the point that centimeter, millimeter accuracy, both relative and absolute, are extremely important. And we think that high accuracy is going to continue to push the value of what UAS systems can do. The availability of high accuracy GPS sensors, the dual band sensors that complement the relative accuracy of the sensors working together really open up new markets that are really demanding this level of accuracy to satisfy a lot of their needs for automated asset management, automated maintenance, relative, I say virtual reality, augmented reality applications. There's so much more of that going into play right now, and you've got to have these accurate models to do it. And frankly, it's really critical to the success of the UAS applications in some major markets. So with that, I will turn it back over to you, General Paz.
Jay, thank you very much. That was fascinating. All right, I'm going to turn it back over to you, Lori. We're going to do a poll real quick, right?
All right, sure thing. See, coming up on our last poll, should see that on the screen right now. We'd like to hear from you. Again, giving you the option to select your top two. The most important factors in determining which positioning solution to utilize are, and we've got their form factor, size, weight, and power, post-processing software, repeatability and stability, ease of integration, or cost. And it looks like we've got 48% coming in with form factor, size, weight, and power, 23% post-processing software, 61% repeatability and stability, 33% ease of integration, and 51% indicating cost. Thanks all for participating in that poll, and we're going to go ahead to for more information slide. So back to you, General Paz.
All righty, great. Yeah, and so here is all of the links for InsideGNSS, Inside Unmanned, our sponsors at Trimble, you know, how to get a hold of their webpage and how to get them on LinkedIn. And then we've got emails for our erstwhile panelists there. So everything you need to know on how to contact folks all on one slide. Okay, so what is next? I believe we have another time for questions still.
Yes, we do.
Okay. All right, so I'm going to go and put Jay Tilley on the hot seat to begin with. Jay, I know that you mess around with an off-the-shelf Matrice 600, but I also know that you know, high precision dual-channel RTK nav is very important for folks. Do you have any advice for folks that are, you know, designing or configuring UAS platforms on how to get the best accuracy from their system?
Yes, Joe Boss, thanks for the question. So there's really, in terms of relative and absolute accuracy, there's a combination of things. I mentioned a couple times in my presentation the importance of calibration. I think a lot of UAS users do not investigate to the great extent they can the camera calibration of their system. And I will say that is just imperative to understand your focal lengths, your angles, your distortions, and be able to put that information into your correction software to get the real value of that. So we do calibration, I said, on the ground and in flight, and even in flight is important. So you might take a few images and process those separately to get the offsets to your factory calibration, and that's often a big help in terms of creating very good, very precise point clouds. Another thing that's overlooked a bit is image quality at edges. A lot of the cameras fall off from their performance at edges. Sometimes they're twice as bad at the edge as they are at the center of their field of view. So you have to take a quick look at that and understand what your performance is there. I will say another thing that's often overlooked is the flight plan, particularly if you're collecting 3D models. Us in the mapping side have come up, we typically like to fly racetrack configurations, so your same altitude going back and forth, but in 3D data collection, the game is very different. You don't necessarily use a racetrack application. You've got to make sure you generate one collection point, or 3 collection points for every point pixel on your 3D object, and you have to be aware of the shape of your 3D object as you do your flight plan. So the flight plan is a particularly important thing, and then I want to really foot stomp what's been talked about already is EMI effects. EMI effects on the system can so distort and it's not just the GPS, it can affect your camera as well, and particularly in terms of signals, so you want to make sure that you have done a good EMI survey of your platform. So those are things that are in the recipe that we have found have been most critical to success of getting accuracy.
All right, very eloquent answer. All right, Stuart, I tell you, I was a little shocked at how big of a problem our audience perceived multipath being. Can you explain how a high-end receiver is going to mitigate multipath?
Sure, thanks, General Poss. Well, let's first of all define what multipath is. So this is where the satellite transmits a signal. You expect to get a straight path, direct signal to the receiver, to the antenna. Multipath is where you also get that signal is going to also radiate to the surrounding area, and it bounces off a building, off the ground, and also is received into the antenna. So you've got the direct and one or more secondary signals with increased path length. There's always going to be a longer delay because there's always got extra path length to get to the receiver. Now, for RTK systems, you've got two challenges because you've got the base, that's static usually, and one of the problems is multipath for a static observer is actually the hardest to get rid of in a lot of respects, because if you think about the geometry, when the satellite's moving relatively fast, but it's got relatively not well-behaved dynamics. And so what you see is that a lot of the bounds will be from around the antenna, from the ground, or things very close to the antenna. And if you work the geometry out, that's a very low frequency change. So the multipath that you get at the base has a very, very slow time-changing effect. Now, at the UAV, it really depends what you're doing with the UAV. So we have properties of the code where if the delay is more than 300 meters, and it varies a little bit based on your signal processing and the satellite signal you're tracking, but if the extra path lengths beyond about 300 meters, it just doesn't affect the signal so far. UAVs that are very high, you're not going to get ground bouncers, but you may get some bouncers from on the platform itself. Also, when you're moving fast, if that path length is changing rapidly, the multipath is there, but it may be that the tracking loop smooths it out. Now, if it's zero mean, then it effectively is eliminated. But if it's not zero mean, you get a bias. Now, what do we do to eliminate the multipath? Well, there's several things. First of all, careful selection of the antenna. So for precision applications, we tend to try and use an antenna that only receives the upper hemisphere. The satellites are not coming from below you. Now, nothing's got a perfect upper hemisphere reception. It will still receive things from below the antenna, but that's the first thing you can do. Make sure you've got an antenna that's receiving the polarization from the satellite. When the satellite bounces, the polarization can shift depending on the angle of incidence and the properties. So that's the other thing you can do. Then at the signal processing level, there's a very simple way to track the signal. You measure the range from a few replicas of the transmitted code. You know what the satellite transmitted. You have a few replicas. You subtract one from the other. You form an error function and drive that to zero. What we've been doing for 20 plus years and refined this many times since then is to actually add extra hardware resources at the problem and use some DSP techniques where we can look at deformation of the signal, and from that attempt to mitigate the multipath signal. So that's the somewhat short answer. So back to you, General Poss.
Very well explained. Okay, Howard, I've got one for you, and I have to admit this one is near and dear to my heart. So do you see a time when GNSS receivers used in UAVs are going to need to comply with standards required for manned aircraft, like DO-160 for environmental specs, DO-178 for airborne software, or DO-250 for avionics hardware? And I would ask you to make a difference between small UAS under 55 pounds and large UAS over 55 pounds.
Sure, and this is a very good question, and there's lots of the whole regulatory question and the certification question is still very, very much up in the air, and I think that it's still not clear what sort of standards are going to be required. But one thing is, you're not just asking whether the GNSS receiver needs to be certified, because it's of no value to have the GNSS receiver certified and everything else is uncertified. Really, everything has to be certified. And so, you know, I'm not so sure that the dual frequency RTK, that there will ever be enough market demand to justify the very high cost of certifying the dual frequency RTK GNSS receivers. However, you know, it's certainly possible to have two receivers on board, a certified receiver and then your higher accuracy receiver. And that might be a much more practical way to approach it than trying to certify the smaller receivers. So that's basically my view on that subject, General Poss.
Wow, that's a great way around it. I didn't think about having, you know, two in there. I mean, my concern is you hear an awful lot about, you know, going to performance-based standards from the FAA. I'm not seeing a lot of those standards yet. I know you guys in Micropilot are particularly ensconced in the DO 178 standards, but I remain convinced that for the large UAS, they're going to apply generally manned manned aircraft standards to receivers out there, but I could be wrong. Okay, Stuart, we got another one here, and actually there's been a couple questions about this. So how does a dual frequency receiver compare to a single frequency receiver in an RF jamming environment, something where they're purposely you know, putting RF energy in their device multipath?
Sure. So, well, at a gross level, you're exposing the receiver to not only L1 but L2. So you've got twice the vulnerability there. However, when you're jammed on L2, it doesn't mean that L1 is going to go away, and vice versa. So there is more susceptibility just because you've got more. You're open to more frequencies. Of course, if the attacker knows what frequency you're open to, that really isn't a disadvantage. The other issue is the precision receivers do tend to be a little bit wider band. It's one of the reasons and one of the ways that we get a little bit more performance. So those bands are open a little bit wider. That does again cause you some more susceptibility. But some of the challenges you have are actually upfront from the receiver. One of the challenges we see are the LNA that's in the antenna. So often people will put in a very sophisticated GNSS receiver and then skimp on the cost of the antenna. And a lot of those LNAs really aren't very robust when there's a jammer. They have a very poor 1 dB compression point, and so when the jammer comes in, the GNSS receiver could actually process it if it had a good LNA, but the LNA starts to saturate before we even see the signal. So yes, there is a little bit more vulnerability because you're open to more spectrum, but you know, we can counteract many of those effects. So back to you, General Poss.
All right, thank you very much, Stuart. Okay, and we get time for one last question. And Jay, you know, you mentioned 3D modeling a couple times in your presentation, but no kidding, how do you see specifically 3D models versus 2D models as becoming more valuable in the UAS markets? And really, how does this better data accuracy improve customer data value? I mean, you mentioned it a little bit, but I was kind of looking at a lot of your stuff and thinking, well, gosh, you know, couldn't a simple high-resolution 2D picture do the same thing that you're talking about?
It's a great question, and of course, to me, it's pivotal in terms of the growth of the UAS industry, and particularly the commercial markets, including some I haven't mentioned, which are BIM and CAD, and particularly in commercial construction areas. If I could use that to answer the question, the alignment of a data set to a CAD model, so as built versus design, is crucial to be able, because we know that about almost 25% of the buildings as they're constructed, our structures constructed, change as they go through that process. A lot of decisions are made in the field that are not reflected in the design. So the as-built matching to the existing design is crucial for efficient updates of the CAD models and the BIM model, the building information model that goes with this building after it's delivered to maintain it, renovate it, and and basically, and there's millions and millions of dollars involved in terms of, which is why BIM is now mandated in federal in the United States. So BIM is one answer to the question. The other part I alluded to in the presentation is the asset management side, being able to identify objects. Really very difficult to do in 2D. We actually tried that on the cell tower side, is trying to do 2D measurements and the asset accuracy that we were getting was pretty low. It's like 70-80%. When you go to 3D, you're more in the 95 to 99% in terms of matching accuracies to your catalog. Now, telecom is not too difficult because there's not that many providers of components to that industry, but in oil and gas, a whole different story. Those measurements are crucial in 3D, and if you're going to be matching it to an asset catalog and doing the type of virtual reality, augmented reality, work at your desk type of operation that a lot of these industries are going to, and particularly on the collaboration side. So the bottom line is that 3D gives you a huge multiplier leverage in terms of the value of that data set the UAS collects over the 2D image. I mean, a crime scene analysis has been doing this for years very effectively in terms of using 3D from UAS systems and others to get that, exploiting that accuracy. We're just trying to do it on a much larger scale, and I think as we do that, we're going to see huge growth and pull on the UAS systems, as we're actually seeing already.
Great answer, Jay. And I got to tell you, as a man who just had a big hole in his roof found and fixed, I would really wish that you would get 3D to the roofing industry, because I had to call 2 roofers out, and one finally found it by poking his finger in it. And I think a 3D system would have found it. All right, folks, unfortunately, that's all the time we've got for questions today. I really learned a lot about RTK GNSS and the advantages of 1 versus 2 frequency receivers. So I really thank our panelists, Stuart, Howard, and Jay. You gave a great presentation. And Lori, I'm going to turn it over to you for our final comments.
All right, thank you. And thanks all. Trust you found today to be of value, and as well, special thanks to our distinguished panel members and of course our sponsor Trimble, co-hosts InsideGNSS and Inside Unmanned Systems. Thanks for joining us. This is Lori Dearman saying, hope we see you on the next one. Have a great rest of your day. Bye for now.